Okay, folks, it's about 3 o'clock. We'll see if Dr. Hainline is over here. But welcome to Bryce Canyon National Park. Here's Dr. Hainline. He is an expert in active galactic nuclei and kind of the formation of galaxies. He works at the University of Arizona and Steward Observatory. So at that point, I'll hand it off to Dr. Hainline here, and he's going to share with us some science that's going to be happening with the James Webb Space Telescope project.
Hi, everybody. I can't see you, so I'm assuming you're all down there, and I want to say hi. I'm talking to you not from Arizona where I live, but actually from Toronto, Ontario, because I'm here giving a series of talks. And I've had to jerry-rig a green screen with some fabric behind me, which is allowing me to do all this. But I'm really excited to talk with you all today, and I'm really excited about this project. And I also hope that we can get through this, and if you have questions, we can answer some questions at the end. But today I wanted to talk to you about this amazing telescope that I've been working on with a lot of people, and some of how it was designed and why it's like it is, and what we're hoping to do. But really, if I shrink myself down a little bit like this, as was said, I'm a JWST NearCam project scientist. By the end of this, you'll know what that means. And it says here at the University of Arizona, but I'm not here at the University of Arizona right now. And this afternoon, we're going to look at these 4 big astronomy questions. Okay, are you ready for these 4 really big questions? Here's the first one. The first one is why, and I told you they'd be big. Hopefully this is projected really big in the room, and it makes kind of people laugh that it's a big question. Why? Another one of these questions is how. Big question, how. Then we have another question here, which is what. And then finally, as you might predict, the last big question we'll be trying to answer tonight is when. And I apologize that maybe the slides are out of sync with what I'm saying. This is a technological issue. So let's actually take that first question and look at it a little more specifically. I should be a little more specific about what that means. So when I say why, I mean, why do we build space telescopes? And why do we build telescopes at all? And why do we need to look at the universe? And why do we study astronomy? These are like pretty big questions. And maybe you look at these questions and you know the answers already. But maybe you're someone who's come here with someone who knows the answers already. And you're like, I actually don't know why we build space telescopes or why we look at the universe outside of just a novelty. And so to that end, I want to answer these questions. And I want to start with a picture of this right here. And this is a picture of the Earth seen from the International Space Station. You can see a part of the International Space Station on the left and one of the solar panels on the right. And I like showing the Earth because the Earth is the kind of foundation of astronomy, right? Not only the foundation of human beings, but the foundation of astronomy, in that the weirdness and diversity and interesting biodiversity and life on the Earth leads us to a bunch of really interesting questions about whether or not the Earth is alone and what's going on outside of the Earth. And we live on a very thin onion layer, like very, very thin, only some number of miles above us and below us in the crust on this one planet here. And you can see the edge. I show this picture because you can see the edge in the atmosphere is very, very thin, right? This very thin layer. And when you look at that and look at the crazy, types of life and plants and water and elements and, like different climates, you might look at that and think, is that everything? Is there something else going on? And that's kind of the foundation of human beings on trying to understand our place in the universe. Essentially, it comes from this idea of, wow, things are so varied and interesting and diverse and weird. What does that mean for who we are and for what we might become and where we came from? And ancient people looked up in the night sky and looked at the stars, and they also noticed a set of objects that moved in a different way than the stars moved. The stars would go up, rise in the east and set in the west every night. And the ancient people noticed that there were other objects that wandered along that, and they gave those objects special names. And the word wanderer in ancient Greek is planet. So here are the other planets in the solar system, of which Mercury, Venus, Mars, Jupiter, and Saturn were known since antiquity for the entirety of human civilization. We've known about those planets because you can see them with your eyes. And it was only later in the 1800s that we discovered, like we discovered Uranus and Neptune, which are a little farther out. And you can't see them with your eyes at night. But these planets here, by observing them over the last 1,000 years and their patterns, and then when Galileo first used a telescope to look at Jupiter and Saturn, we start to notice that these planets are very different from our planet. They, in some cases, are much larger. So you can see here, Jupiter, about 1,000 Earths could fit inside of Jupiter. Saturn has those beautiful rings, right? None of them have the surface that looks like it has water on it. And in fact, that's true. None of them do have water flowing on the surface. Jupiter, Saturn, Uranus, and Neptune are much larger because they're gaseous. Right? These differences lead us to want to go, wow, why? Why is that like that? And are these planets the only thing we see? And we can actually keep looking with telescopes as telescope technologies progress farther and farther to try and understand, well, what else is out there, right? We see beautiful images like the images here that I'm showing, which are images showing like these fuzzy things that we call nebula. And astronomers weren't when we first named nebula, the word nebula just means fuzzy. And it was because when they were first seen, literally, they just looked through a telescope and it wasn't a little pinpoint like a star, it was fuzzy. So we were like, well, that's what we'll call it. And so these nebula, when we look at it with better telescopes, we can see that what they actually are is sites of stars being formed. It's where baby stars are being formed and lighting up the gas that you're seeing there. So this is gas and dust on the left. And if you were to zoom in on one of these stars, you could actually see a star being born on the right, where you can't actually see the star being born. It's in the very center of a disk around it and has this jet that's kind of coming out of it that's extending down and to the left there. And when we use telescopes and we start looking farther and farther, we start seeing that, all of these stars and this gas and these things we're seeing are actually inside of something very large that only was really understood in the 1920s. But like the Milky Way galaxy, this incredible grouping of 100 billion stars. And when we look with telescopes, we can see other galaxies, like this galaxy here, which is very similar to the Milky Way. We don't have pictures of the Milky Way because we live inside of it, but this is similar to the Milky Way in that it's a spiral galaxy where you see all the little dots and stuff in this are individual stars or clusters of stars. And there's, again, 100 billion stars. You see dust, that's the kind of brown webbing that stretches between things. You can see that there's regions where there's not as many stars. In the center, it's a little yellower. It tells you something about the stars. And astronomers, over the last 1,000 years, started really piecing together this puzzle of what's out there and linking it to an evolution of the universe, a change from the beginning of time to now in structure, in content, in diversity. And if you would even go farther out, you'd notice that our galaxy, the Milky Way, and nearby galaxies are one tiny chunk of the universe. And if you look at it with a telescope in any given direction, you'd see that there's galaxies everywhere. This is a very famous picture that I'll come back to called the Hubble Ultra Deep Field. And the Hubble Ultra Deep Field, every object in this, except the ones that have like little spikes coming out of them, you can see one in the center. I don't know if you can see my mouse, and then there's one at the bottom there. Every other object in here that isn't a star, which is the ones with the spikes, is a galaxy, like what I'm showing you here, except seen from very, 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 very far away. And this type of image is the type of images that astronomers use to look back to all the way to as far as we can towards the beginning of the universe, towards the earliest galaxies. And this is a very, very quick overview to just this idea of the reason we study astronomy is because we start with an Earth, a little pristine ball in a giant, enormous universe, and wonder, how did it get here? How did we get here? And the answer is a journey of billions of years. And one of the other things that we learn about this comes out in chemistry. So this is something that maybe you might have some like fears over, remembering when you were in elementary school and this was hung on a wall. But don't worry, we're not going to go through this too deeply. But this is the periodic table of the elements. It's essentially all of the known elements. I think I might be in the way of a couple of them, so I'm going to make myself disappear for a second. All of the known elements. And the simplest elements are up on the top, essentially. Up in the top left is an element hydrogen, and in the top right is an element helium. These are pretty classic elements that were helium mostly, it goes into balloons, but it's a very light element. It's only 2 little protons, and hydrogen is just 1 proton. The number above tells you how many protons are in the nucleus. But you can see some other classics like carbon, nitrogen, oxygen as 6, 7, 8. These are important. Your fingers are made out of a lot of these things. Things like gold and silver are 47, 79, right? I guess 79 and 47 if I say gold and silver. But this is essentially everything that you know is made up of these elements. That's what's cool about these elements. The way they're colored is by the method that the universe used to build these elements, which I think is really amazing. So I'm going to transition the slide, and you're going to see how this periodic table is special, because this is kind of the astronomy periodic table, where in the top left, you can see it says Big Bang fusion. That means that the Big Bang, the very beginning of the universe, that produced these elements. And there's only like a couple that were produced in the Big Bang: hydrogen, helium, and a little tiny bit of lithium, number 3. But when you see other things like exploding massive stars, that's the green. All the green you see required a star to explode. Carbon, nitrogen, the oxygen you're breathing right now was once inside of a star, made and generated in the very core of the star. And then when the star died, it gave off its material in an explosion, and that material is what you're currently breathing, which is amazing. Or dying low mass stars like our sun, which create a lot of carbon in its core. And when they die, in that process of death, it pushes out a bunch of gas that also makes a lot of the carbon that your fingers and hands and body is made out of, which is amazing. I really like the orange, where you can see gold and silver are primarily orange, where it says merging neutron stars. And we think that the majority of the gold and silver, like the silver in my wedding ring right here, is created when 2 stars, very massive stars, live their entire lives, each individually blowing up at some point in their lives, but still their nuclei, the cores of those stars after they've died, continue going around each other, and then eventually they crash into each other and explode. In that process, that creates the gold and silver and all of these heavy elements that you see. And we just wear them as rings. This is the evidence of stars that lived and died in a binary pair and crashed into each other billions of years ago. And I show this because this is chemistry and it's biology right here. And it all comes from astronomy. And understanding the process that built us up from simple elements to more complicated elements, that's one of the goals of astronomy. It's the foundation of quite a few other sciences, right? So with that in mind, I want to talk about why we build telescopes for astronomy. And to start with that, I want to talk about the human eye. The human eye is this beautiful creation, really, really amazing how it works. But the problem is that a human eye only has a very specific resolution. If I hold a penny up to your eye, it looks larger because when it goes through the lens, a large image appears on your retina. And that large image is interpreted by your brain as, oh, this is a penny, right? Also, it's upside down, if you can notice that on the right. Most people don't realize that your brain flips the image back the right way. Thank goodness, brain. If you took the penny a lot farther away, you'd notice that the penny looks smaller because it made a smaller image on our eye. So if you want to look at something really, really, really far away, the image on the retina is really, really, really tiny. And that's not great because our retina only has a certain number of cells that can detect light, okay? And so this is why objects look smaller and have, are more fuzzy, the farther away they are, because our eyes aren't super, super highly sensitive. There's only so many little cells. If you remember when we were advertising digital cameras, they would talk about megapixels, the millions of pixels, right? And like, if you had a larger number of, or a smaller number of large pixels, you wouldn't get as good resolution. If you have a lot of very small pixels, your resolution would increase because even with a tiny image, you can image it across a number of pixels. A telescope essentially allows us to take something very far away and image it on our retina larger, okay? It's a way of taking something very far away and doing what we're doing with the top image. So let me explain that a little bit more. This is a classic image of a telescope. This is a telescope that's called the Newtonian reflector. Some telescopes use mirrors. This telescope, some telescopes use lenses. This telescope in the image here uses a mirror. But what the lenses or the mirror do is it focuses light. It focuses light into a false image. So if you've ever used a magnifying lens, and I had a bunch as a kid, like I had a book called the Explorer book that was like my favorite book in the world, that had a big page with a Fresnel lens, this big flat lens that I just used to look at everything. But if you ever use like a magnifying lens, you'll notice that, magnifying lens makes the object you're looking at, like your hand or an ant or something, look very large, right? But if you move it too far away from the object inverts and gets blurry. And that's because there's only a limited region with which a magnifying lens can work and increase things. So what a telescope literally does is it takes the faraway universe and focuses it such that a magnifying lens can then work on it. And so there's a secondary lens. You can see the lens right near the eyepiece where the person is looking into it. And that lens is just a magnifying lens, but it's taking an image of the faraway galaxy, which has been focused to a point. It's taking that image and increasing it for our eyes. So a telescope is just a magnifying lens attached to another focusing element, in this case a mirror, to take the faraway universe, capture a lot of light, and shrink it down to a virtual image that can then be increased with a magnifying lens. And so this is the foundation of modern astronomy, is when this was created. Before we had telescopes, we did a lot of astronomy with naked eye astronomy, and really large. There's a very famous astronomer named Tycho Brahe who had this very large room-sized instrument that allowed him to, with a slit in the wall, allowed him to very carefully measure the positions of stars in the sky. But he had to do it all by eye. Had to move his head and move the instruments to look through them, but there was no magnification. And Galileo and some other people, but Galileo is the most famous one, took some of the first telescopes, which had lenses, to look up at the planets and the stars and changed astronomy back in the 1600s. So why that matters is because if we want to take a picture like this and really zoom in and get really details on all of these things, we need to be able to have big telescopes to essentially create that virtual image and then allow us to magnify it, because this image on the sky, this is pretty tiny, right? So I'm gonna shrink this Hubble Deep Field out so it's the actual size that it exists on the sky. And so hopefully that animation was smooth. If it wasn't, I apologize. But you can see that this deep field, which in here is called the XDF, the extreme deep field, is so much tinier than the moon, right? So sitting on the Earth, you standing on the Earth and looking up at the moon, you can know how big the moon is, right? Like you could put your thumb over the moon, if you wanted to. And then that tiny little patch, that's the deep field that we were looking at. And that's actually a pretty large patch compared with things that, many astronomers have studied, much, much smaller things. When we look at images from that, we only look at very specific galaxies and parts of those galaxies. So you can imagine that tiny, tiny fraction of an angle on the sky having to be magnified and magnified. You need a pretty big telescope to be able to do that. So here are some examples of large telescopes that allow us to do these sorts of things. This is a telescope that's in Arizona near where I live on a mountain called Mount Hopkins. This is the MMT, which has a mirror that's about 6 meters in diameter. And here's another very famous telescope mirror. This is on the Keck telescope in Hawaii on the summit of Mauna Kea. And this is a 10-meter telescope, which has these hexagonal mirror segments. But you can see a very large mirror is pretty helpful because that allows us to get even better resolution. And every second, more light hits the mirror, so you don't have to take as long of exposures to get the same amount of light as you would with a smaller telescope. And then here's a very famous telescope that has a pretty big mirror, 2.4 meters mirror. This is the Hubble Space Telescope that you may have heard about. A lot of people, I think it's one of the more famous space telescopes. The Hubble Space Telescope is a telescope that was launched in 1990. I'll talk about that in a second, and or a little bit later. And it has a 2.4 meter mirror, so it's a little bit, the mirror diameter is a little bit taller than Shaquille O'Neal. If you could imagine a basketball player, it's a little taller than a very tall basketball player. And it's about the size of a school bus. We'll show that in a second. And it orbits the Earth. And it has taken images with its incredible mirror like these. These are some of the more famous images that Hubble has ever taken. This on the left is an image called the Pillars of Creation. And similar to what I was showing you with the gas cloud, it's a site of baby stars being formed. And the stars, when they're born, when you have very, very hot stars, those stars, they have a cosmic wind that pushes gas away. And so what you're seeing here is a bunch of baby stars are above the image, pushing the gas away, leaving denser pockets of gas, these fingers of dense gas where other baby stars are being formed. And on the right, this is another famous image called the Horsehead Nebula, and it's another star-forming region. But you need a pretty good telescope to do this. And what's amazing about the Hubble Space Telescope versus Keck or the MMT I was showing earlier is that it's in space. And space does not have the same atmospheric blurring that the people on the ground have to deal with. If you've ever gone outside at night and looked at stars, you notice that they'll twinkle. We sing a song about it. That twinkling is actually wonderful for the charming song, but really annoying for astronomers because it's the air blurring the light. Like if you're in the desert and you look out over the desert and you see that there's like shimmering in the distance like a mirage. That is atmosphere, the hot atmosphere, causing shimmering and moving the light around. And that's pretty bad if you want a really crystal clear, high resolution image. So if you put a telescope in space, you can get that, which is what you're seeing here. Incredible optics. As I said, here's the size of the Hubble Space Telescope. It's a little bit bigger than a bus here. I like this image because they put the name Hubble on the bus. If you've ever gone to the Smithsonian Air and Space Museum in Washington, D.C., they have a model of what the Hubble Space Telescope size is. It orbits our Earth, so we've gone out and serviced it a couple times. Again, here's the mirror next to some people. If you remember, if you're old enough to remember, when the mirror was milled initially, it was milled a little bit off, so there was a little bit of astigmatism to it, and it had to be corrected by going up and installing a new kind of set of glasses, but like an optical element that helped correct that mirror imperfection. And Hubble operates at a very, this is one of the more technical diagrams in this talk, and I apologize for that. But Hubble operates at a wavelength range in what we call the optical and a little bit into the UV and infrared. So let me explain. On the far left, where it says wavelength, and there's like, like a set of boxes that say gamma, X-ray, UV, IR, radio. That's the spectrum of electromagnetic radiation. And electromagnetic radiation is the really complicated way, if you want to sound smart, of saying light. And all of the things there, gamma, X-ray, UV, IR, radio, those are light. And you're saying, wait, radio is light? And it is, because most people think, just naively, radio is sound. Radio that you hear, like when you turn on radio in a car or in your house, that radio is sound, but the way that the radio has come into your house or your car is through light waves. The antenna on your car is just picking up very long wavelength light waves. I have my cell phone here, and a cell phone is also has an antenna in it that's just picking up radio waves, wavelengths of light. And so that's how we send a lot of signals around the world, is that when you have X-rays, like an X-ray, I have had a lot of tooth stuff going on this year, and I had to have a lot of mouth X-rays. And that's just a fancy flashlight that's shooting very powerful, high energy light that goes through our body, but is stopped by our bones. And that's X-ray light. And that's a very dangerous gamma, X-ray, these high energy light, that can be very dangerous to us, which is why you wear those like lead aprons and stuff when you're getting dental X-rays. The light we see is just a little rainbow you can see there in the very center. That's optical light, optical from the eye, because it's the light our eyes can see. And it's a very, very small window of the universe's diversity of light. Red, orange, yellow, green, blue, indigo, violet, your kind of classics. Just shortward of that, at shorter wavelengths, is ultraviolet, which is the type of light that you wear sunscreen to reflect, because the sun gives off some ultraviolet light, and it's actually pretty bad for us. So you wear sunscreen, and the sunscreen essentially just reflects ultraviolet light, so it doesn't hurt our skin. And just at longer wavelengths is infrared. And so you can see they've zoomed in around the optical region, and you can see that the wavelength numbers in nanometers there, infrared starts at maybe 700 or 800 nanometers and goes on all the way to 10s to 20s of microns, which is a larger unit than a nanometer, so thousands and thousands of nanometers. And Hubble has instruments, you can see them all labeled there. COS, fine guidance sensor, and NICMOS were some of the original instruments. NICMOS was a near-infrared camera that they've actually just turned on for the first time in a decade, just like a couple days ago, because the Hubble Space Telescope is currently in safe mode because they're trying to figure out what's going on with some of the instruments. It's a 30-year-old telescope in space. And NICMOS has been replaced by an instrument that you see in green, the arrow that says WFC3, or down on the bottom right. WFC3 has mostly replaced NICMOS, but they had to turn NICMOS on for the first time in 10 years, and it's very charming for us astronomers because it's an old instrument that doesn't get used anymore. To have them turn it on just to see how it's still working is pretty fun. But all these instruments, mostly the ones that get used are STIS, WFC3, ACS, and COS, and those all operate UV and a little bit into the infrared. Right? So that's the wavelength range of Hubble. And if I come to this, the universe is doing something really interesting with light, which is that when you have in the top panel, you see galaxy at rest, it's giving off lights to the Hubble Space Telescope, a galaxy just sitting like near us, like Andromeda, that's not particularly moving very fast compared with us. You'd look at that and you'd measure it. You could take its light and pass it through a prism, like you can see in that little rainbow with the 3 lines there. And that's pretty cool. Those lines are absorption from gas in the galaxy. If the galaxy were coming towards us, which is actually what Andromeda is, and there are many that are coming towards us, just because of the way the galaxies move in the universe nearby. If it's coming towards us, it's similar to how if you are listening to, say, a train that's going to come by, has a horn or something, or a siren. I'm going to do this. Hopefully it translates well over the audio to you all in theater there. But the sound that it goes, and hopefully you've heard this, is like a siren. Like that shifts as it goes away from you. And that's because when the siren is coming towards you, the train, that sound is compressed. The wavelengths are pushed together and it's shifted to a higher pitch. And when it's moving away from you, it's shifted to a lower pitch. And that right there is called Doppler shift, and it happens with light as well, meaning the galaxy that's coming towards us, its light is compressed, the wavelengths are compressed, so those 3 lines are pushed towards the blue. But if the galaxy is moving away from us, its wavelengths of light are moved towards the red. And this is what's happening to most of the universe, because most of the universe, in an expanding universe, we feel like we're in the very center. We're not. We just don't feel our own motion through the universe. Everything else seems to be expanding away from us. And the farther things are, the faster they're moving away from us, meaning their light is redshifted more and more and more. And that matters because if you want to look at really, really far away things, all of the light that we care about is shifted out of the optical into the infrared. So if I go back to this diagram, you could imagine we care about things in the optical, and if it's pushed out to the infrared enough, maybe it's beyond what WFC3 can see on Hubble, right? Maybe it's beyond what NICMOS can see even. Maybe the light that we care about is at 3,000 nanometers, and Hubble could not see it. So Hubble is limited by the fact that it doesn't have instruments that go into the infrared. And that's a really key place for a lot of science that we're going to talk about. So this leads up some questions, or how questions, okay? How do we design a successor to Hubble? As I said, Hubble's been up there for 30 years, 31 years, and it needs a successor, something that will carry on Hubble's scientific achievements into the next decade and beyond. How do you build something like that? How would a telescope like that work? And how cool would it be? Very cool. The answer is very cool. So ideally, we'd want a telescope with a larger mirror, something bigger than what Hubble's is, because that allows us to get more light per second and also better resolution, and maybe instruments that were focused on the infrared portion of the electromagnetic spectrum, something where Hubble's doing a pretty good job at shorter wavelengths. Let's go to where Hubble cannot look, but where there's a wealth of information. To observe the infrared, it would have to be very, very cold, and if it were larger, it had to be able to be folded up somehow to fit inside of a rocket. So this gives us some challenges, right? We need something that's going to be cold and sitting inside of a rocket, which is kind of tough. So let me bring myself back here now that I've done this, because I like being able to see you, especially because I've been gesticulating. You probably haven't seen it. So here's a really cool diagram that I put in here that maybe you probably haven't seen, but these are some proposed ideas back in the early 90s and on to around 2000 of what a successor to the Hubble Space Telescope might be. So this is a drawing straight above me, and you see some other like diagrams over here from different companies who are proposing to NASA, hey, if you want to build this telescope, here's how you might want to build it. And most of them you can see have a mirror that looks like it's foldable in some way, like the one that's right above my head. You can see these little pedal arms that look like they could fold out, right? And the one that says NASA Goddard there also has a very similar thing. The one that says TRW has a foldable mirror, and then they also seem to have like some sort of paddle or like shield, right? The NASA Goddard one has a very specific type of shield, and the Ball Aerospace one has this silver shield. The TRW one has a shield. The Lockheed Martin one has a shield that's a big pink thing in this diagram. But you can see that all these seem to have these kind of similar components in that you'd want it to have a shield and then this foldable mirror, right? Eventually, this is the design that was settled upon. And so you can see very similarly, there is a big mirror And we'll show you exactly how big it is in a second. It's hexagonal segmented, kind of like the Keck telescopes are, right? So it can be assembled not as just one mirror, but as a bunch of individual mirrors. And then there's this big pink and gray like shield underneath it that was seen in the earlier designs. And you can't see it now, but the sides of the mirror and the secondary mirror, that big thing on arms that comes out, those sides of the mirror fold in, right? So this whole telescope design, the JWST, was designed to also fold up and have this shield. Here's the comparison of the size of the Hubble Space Telescope and JWST, and you can see it's significantly larger. So it's 3.5 Shaquille O'Neals tall. Or if you use R2-D2 as your standard unit, it's about 6 R2-D2s. Or maybe you're very familiar with Mount Rushmore. It's the size of George Washington's nose on Mount Rushmore. Maybe you just want a number. It's 6.5 meters in diameter, which is about 21 to 22 feet. And it's an amazingly, like, it's something to really be seen. I was very lucky to be present as they were assembling it, doing some testing on the instrument that I work on while they were assembling it. It was a marvel to watch them painstakingly assemble each mirror segment. And I've seen it once fully assembled when it was at Northrop Grumman in California, and it took my breath away. It's a huge mirror, and the mirror is gold plated. So you can see here, this is a picture from Goddard Space Flight Center after they assembled the mirror, and then the pictures of the actual assembly process. And on the right, you can see the mirror covers are still on. They took the mirror covers off after they assembled everything. But the mirrors are gold plated. The total amount of gold, if you were to take it off and melt it down, is maybe the size of a golf ball. So it's a very thin layer of gold across such a large area. But gold reflects infrared light really, really well, which is why we've plated it in gold, not just because it looks really epic. And then it has these arms on the top, and those hold the secondary mirror, which you can see in the top left corner. Hopefully you can see it's like a little round secondary mirror, and that's the light that after it bounces off the primary mirror, it bounces off the secondary mirror and goes into that little like ziggurat in the center, which is called the aft optic subsystem. There are 4 instruments that are on board JWST. There's NearCam, there's MIRI, there's NearSpec, and NEARES. NearCam I'll talk about in a second. MIRI is a joint effort of Europeans and Americans, and it is an instrument that's at the longest wavelengths. It's the mid-infrared, which is where the M in MIRI comes from, MIRI, mid-infrared instrument. NearSpec is a European instrument that is like a very, very fancy and expensive prism for the light, allows us to take incoming light from the universe and spread it out by its component wavelengths so we can look at the fingerprints. It's a spectroscope where the word spec comes in there. We can look at the fingerprints of what's in a galaxy and in a star and gas and stuff. It's very, very, very complicated. And the NEARES is a Canadian instrument, and it is the ISS stands for slitless spectrograph, so it actually combines what NearCam does and what NearSpec does, and it has a couple components like capabilities that none of the other instruments have. But all the NI instruments, NearCam, NearSpec, NEARES, operate at very similar wavelengths in the near infrared. So this is just longer than what we can see in the optical. Here's NearCam, and I'm going to make myself go away. No, I'm in a good spot here. Here's NearCam. I move my head so that you can see one of the other pickoff mirrors here. But NearCam, compared with this person here, is a camera. It is the primary imager on board the Space Telescope. It was designed by my coworkers under the guide of my boss, Dr. Marsha Ricci, who's an incredible astronomer. You should go look. She's been interviewed for a lot of things. Most recently, most excitingly for me, was she was interviewed in an August issue of the New Yorker that you can go look at, where she talks a lot about the process of building this telescope, or this instrument. But NearCam is actually 2 instruments sandwiched together. And you probably noticed that it looked like part of what you could see on the top is reflected in the bottom, right? Like there's 2 mirrors above my head, right? And there's 2 round, like they're actually filter wheels, right where the gentleman's hand is. He's grabbing near one of the filter wheels, and below is another one of the filter wheels. And that's because NearCam when it was designed, we want to build 2 identical cameras that are sandwiched on each other to make one rectangular image next to each other. And on top of that, sorry, I should drink some water right now. On top of that, what's also cool is that inside of each of these modules, there's module A and module B, there's a special thing called a dichroic, that the light comes in and is split into a short and a long wavelength channel, like the light is split by its wavelength, so that you can take individual images through 2 different filter wheels at shorter and long wavelengths. So you actually get 4 images at once, 2 of the same part of the sky at short wavelengths, and 2 of a different part of the sky, 2 of the same part of the sky at short wavelengths, 2 of the same part of the sky at long wavelengths. This right here is the sunshade, and the sun shield is looks like it does. Like what it is it allows us to keep the telescope cold. So it's the thing I was saying in all the proposed designs, this shield, it's 5 layers of a very, very thin fabric. And you can see here them testing it, deploying it by pulling it apart. In space, it's going to be robotically deployed, robotically pulled apart, and then all the layers separated. And why it's there is because it keeps the telescope very cold. So you might think, isn't space cold? And technically, yes, but when you're sitting with the sun hitting you all the time, the sun heats you up. And so you can see that on the hot side of the telescope, pointing towards the sun, it's going to be 185 degrees Fahrenheit, or 85 degrees Celsius for the people who I'm here in Canada giving talks about JWST to. But where the sun shield blocks the light, and you don't get the light from the sun or the Earth, it's negative 388 degrees Fahrenheit, or negative 233 degrees Celsius. That's quite a difference. And the reason that we use this to make the telescope cold is because the telescope works in the infrared, right? This is an infrared instrument. These are infrared instruments. When you have infrared instruments, they're looking at light in the infrared. And if you've ever used like night vision goggles or seen night vision goggles that use infrared light, they'll find that when someone is warm, a person, an object, a thing, that warmth of that object will cause it to glow in infrared light. And so if you had a camera that was warm, it would glow while it was trying to take pictures, and some of the light of itself would leak into the camera images, and that would be really bad. You would not want to take a picture of something where you are contributing a lot to the light just by being warm. So we have to keep it all very cold. And in fact, MIRI at longer wavelength has to be very, very, very cold. There's extra coolers for MIRI to keep it cold. Everything else is passively cooled. We say we don't actively cool it, but MIRI we actively cool. Here's another test of the sun shield to show you, they're less than the thickness of a human hair. They're very thin, but they're resilient. And you can see here, this is from 2016, one layer where if I zoom in a little bit on some of these, you can see that there's these like ribbing here that allows it to stay, like if one of the little, like if a micrometeorite or something goes through part of the sun shield, it will still stay tense because it has this ribbing, which allows it to expand in a very specific way. It's a very clever design. So now you're probably looking at this and also going, well, wait a minute, Kevin, you said this has to fit in a rocket. How is something that is the size of a tennis court here, this is not the actual telescope, this is a model in DC that they erected for a festival. How is that going to fit inside of this rocket? So this rocket that you're seeing here is an Ariane 5 rocket launched from French Guiana. This is not the one that will be launching JWST, but it'll look like this. And notice it's very much less than tennis court size. So how do you fit something that is tennis court size inside of that? And the answer is and when Hubble was launched, I should say, it was launched from the space shuttle using this thing called the Canadarm. Can you see this arm here? It says Canada on it. This is a very famous thing that's actually up here in Canada. It's on their one of their $5 notes. It has the Canadarm. They're very proud of this. And it was the arm that helped lift the Hubble Space Telescope into its orbit from the space shuttle. But we don't have space shuttles anymore. We don't have a space shuttle program. So we have to launch it through a rocket. And the way we get it into the rocket is we fold it up. So here's a diagram showing how the JWST folds up to fit inside of a rocket nose cone, right? So you can see here the same rocket I'm showing on the left, and it's all folded up, where the 2 sides of the telescope mirror have folded back on itself. You can see it better on the right. The sunshade is entirely folded up and then folded on the front and the back of the telescope so that it can all sit inside of there. And later on, I'll show you how it deploys. But this is a pretty amazing technological marvel because this all has to unfold and deploy in space, which is in space and robotically. It makes JWST the most complicated thing NASA's ever done. More complicated than putting a person on the moon. This robotic mission, this robotic deployment is going to make my life and many people's lives in the first, like at the end of this year and in the first month of January, really nerve-wracking. So now we arrive at this really big question, which is what can we do with a telescope like this? Given a telescope that operates in the infrared with a big old mirror with, that's very cold in space, what can we do with it? And that's the most exciting question. So we'll start with what I do and what I'm excited about. This right here is, again, the Hubble Ultra Deep Field. And JWST is going to look at galaxy images, look at regions like this. And we're going to look at regions like this and do a better job of actually getting higher resolution. So here, if we zoom in on the galaxy in the very center, above, well, not the very center, but a little above the very center, just to the left of where I have the zoom in, you can see that this galaxy image here is, it's fuzzy. You can kind of tell some stuff about it. But if you simulate what it might look like with JWST, you can suddenly see not only there are a bunch of galaxies around the galaxy you couldn't see before, but also individual clusters of stars and way more structure than you ever could. So JWST will allow us to look at regions we've already looked at with Hubble at better resolution. But then because it's an infrared telescope, it allows us to see way farther back to galaxies that Hubble could not see, that their red light is redshifted out of what Hubble could see into regions where JWST can see, because it's operating wavelength ranges 0.7, 0.8 microns in the near infrared, all the way out to 20 microns and a little farther than that in the infrared. And that's a pretty wide range that allow us to do stuff that Hubble could not ever do. If I show this image here, this image right here is a simulated image from our most recent simulation of a region called the Jades region of the sky. And Jades is it's the JWST Advanced Deep Extragalactic Survey. It's a survey that'll be completed in the first couple of years of the mission. It will represent the largest, deepest, I guess it's not the largest, but it is definitely by far the deepest region that JWST will look at of galaxies. And if I show what I just showed you, which is Hubble's most ultimate ultra deep field, as compared with Jades, which will go deeper at a higher resolution at different wavelengths that Hubble could not get, you see that maybe it's not going to show, but the region that JWST that Jades would cover is some small fraction of this whole image. And I'm not showing you, I couldn't show you the whole thing, but because it stretches up off this, is about half the width of the moon. So you remember earlier that JWST, that the XDF is like some little tiny chunk compared with the moon. Imagine this is half, like the moon would stretch across this twice over. So it's a really big region, and we're very excited because this is only the deepest region. We also have a wider region that's at less deep depth. But this is a simulation that we, from our own internal stuff of what it might look like. And it's just crawling with tens to hundreds of thousands of galaxies. For galaxies closer to home, we'll be able to do even more intricate deep studies of stellar populations. You can see the Whirlpool Galaxy here. We'll be able to really understand that. And more importantly, because infrared light at certain wavelengths allows the dust to pass through it, all of the dust you see on the far left that's making it very red, we'll be able to see through that dust, understand what stars are doing throughout the galaxy, not just in the regions where there's not a lot of dust. And we'll make images like the top right, which are some of the better Hubble images of the early universe galaxies, that allow us to make those images look like the ones in the bottom, where we're also seeing how galaxies collide and crash into each other. And it will give us insights into all manner of galaxies, which is very exciting. Much closer to home, in our own galaxy, we'll be able to, as I said, look through dust. So here's an image taken with both of these images are taken with Hubble. One of them is taken with actually, no, so both these images, I think the one at the bottom is taken with Spitzer, another infrared telescope that was much smaller than JWST. But you can see in the top, you can see a region of stars being formed, but in the bottom, you can actually see all of the stars that you could not see because the dust throughout the image, it's colored here like reddish, but also has some blue. That dust and gas, you can see right through it, see the panoply of stars and the little jet streaming off from the star that's at the very center of this. You can just barely make out in the top image. So infrared light gives us a window in the universe that we have not been able to have at this resolution before. This is an image from Spitzer also that is of like what's called a bow shock, in that a star is kind of plowing through this blue star in the center is plowing through gas and dust and warming it ever so slightly, that where Hubble could not image it, it could not get to those wavelengths to image this dust. And so you're seeing it as it plows through that, and that is important because that compresses things, which helps trigger star formation. And so this is a very pretty image that we'll have a better resolution on, because Spitzer was a smaller telescope than Hubble. We'll be able to really resolve out the fine details in this. One of the other cool things about what JWST will do is also in the hunt for our understanding of extrasolar planets and life in our galaxy. So this is a diagram that shows how when you have a star that's far away outside of our solar system, planets that orbit in a very specific way, they orbit where they block the light of the sun of their host star, and when they go in front of them, when they do that, the light goes through the atmosphere of those planets. And when the light goes through the atmosphere, we can tell things about what's in the atmosphere. So in the very bottom, it's a complicated spectrum. It's like light passing through a prism, like I've said, where we see as a component function of wavelength how bright an atmosphere of this star. This is 8189733, which is this gas giant we show up here. And you can see that all the wiggles that are in the black there, all those wiggles are wiggles from various elements like methane, carbon dioxide, water. And by looking at those wiggles with NearCam and with MIRI, we'll be able to understand the atmospheres of planets outside of our sun, to understand what's going on in those atmospheres. And are there tracers of biological life on those planets, which is pretty cool. Even cooler, I think, maybe I'm biased, I don't know, this isn't exactly my field, but I think it's pretty cool. You can use the fact that we can block the light of stars inside of NearCam with a thing called a coronagraph. So on the very bottom of this slide here, you see a series of coronagraphs, 3 dots and 2 little lines, of which one of those lines, the one in the second from right, is being pictured in the top left, or being simulated in the top left. Those things you can stick right over a bright star. And when you do that, and you do it very cleverly, like you're showing in the panels in the top, you can actually directly image planets, take images of planets. And the thing is that planets are not very bright compared with the stars. All of the weird rainbow patterns that you see in the left and in the far right, those are the fact that even when you put a coronagraph to block the light, it still spills out all over the side. You have to be very clever about removing all of that excess light so you can see the planets. You can take direct images of planets outside of our solar system, faraway planets, so you can understand how they move and what their colors are and whether or not, and if you monitor them, what's maybe going on like on the surface. Pretty cool. In our own solar system, we can take images of planets like Jupiter. Here you see Jupiter in the infrared from a ground-based telescope. So with space, we'll be able to do this with better resolution. And when you look in the infrared, you're looking down into Jupiter where it's a little warmer to see different layers within Jupiter as you march your way down to understand the turbulence of the storms that are going on the surface of Jupiter. Pretty cool. You can even do images of Mars, like this is NICMAS. I was talking about the near-infrared image NICMAS, and we'll be able to use JWST to image Mars as well as Saturn's moon Titan. There's some simulations of what it might look like with JWST. And these are pretty bright images, but we can monitor these planets and these moons to understand their cycles over the course of the year using JWST. So with all this in mind, there's a whole bunch of science it can do. And the question then is, when's it going to launch? I want to know when can we get excited about this telescope? And the answer is December 18th, which is just coming up. And I am very surprised because when I first got this job, it was supposed to be October of 2018, and it's been delayed, but it really does feel like this is actually going to happen next month. And I could not be more excited and also freaked out. Why? Because a lot of stuff has to happen right after launch. This is a diagram showing all of the things that have to happen after launch before it gets to the spot where it's actually going to be. So I'll move my head out of the way. And so you can see that each one of these, it says L plus, that's launch plus. So launch plus 3 minutes in the top left. When it gets at the Earth, it separates from the fairing. Those are the rocket parts that are holding it in, they fall off. And then it separates from the launch vehicle about 30 minutes in. So once it launches, in the half an hour that it'll be left on its own devices. And in 33 minutes, that's when it opens up a solar panel. And we're going to show all of these parts right here. But all this has to happen robotically on its own as it marches out 1 million miles. You can see the moon's orbit is that gray line, right, up in the top left. It has to go, it's not orbiting the Earth. It's going way, way, way far from the Earth, 4 times as far from the Earth as the moon is, to sit in this spot L2 where it's going to orbit, like you can see in that green spot right there. It has to do a very complicated maneuver to kind of park itself and start orbiting like that. And at that point, it will just exist in a line between the Earth and the moon, or the Earth and the sun. It'll be stationed in that spot L2, always pointing its bottom at the Earth and Sun together, because they're the ones that are going to keep it, that would make it warm, and it wants to put the sunshade up to block the light from the Earth and the Sun together. So here's our video, and I really hope that this video looks okay when it's transmitted to you all. It might be a little stutter step, but this is a video showing the actual deployment of the telescope. And so you can see the sunshade and then this little antenna that transmits to us. And this is what's going to happen over the course of the first week, which is right around Christmas time. So it's going to be my Christmas break. It's going to be very nervous as we watch for news of the two sunshade parts, sunshield parts opening up. At this point, it's going to telescope a couple of arms. Sorry, it has to move the primary mirror up on this mast here. And then you're going to see this is the pink sun shield cover that has to open up. Again, this is all robotic on both sides. And I apologize if this is stutter step. You should go and find this on YouTube at some other place, because it's a really wonderful animation that Northrop Grumman put together. And it's going to pull these arms out on either side, tension the sunshade, and then they're going to drive up these little arms on each side to slowly separate all 5 of the very gossamer thin layers. Then Christmas happens. And then we get the secondary mirror deploying there, and then the petals on each side also deploy. And there's many ways in which this could go wrong, and it's pretty scary. But we've tested all of this over and over and over again here on the ground, and they've been tested just now, more recently, as we're getting ready to stick it on the rocket. But that's JWST in space right there, and that will take about a month until it gets all the way out to where it's going to start. Where it's going to situate itself in its orbit, and then we get to go and turn on all the instruments and start the process of calibrating the instruments. So here is what has happened just in the last couple weeks, which is that it was in Los Angeles at Northrop Grumman Space Flight Center. This is the actual telescope here you see now. And it's, at this point, put inside of a unit called the STARS unit, which is like a special safety blanket to hang out, safety container to put it, because we're right now in an incredible clean room with very, very limited dirt and dust at all, particles at all. The STARS containment unit is also very, very clean. A truck drives it out of Northrop Grumman. This is south of LAX airport. And it's going to do this thing that I think is absurd, because I used to live in Los Angeles, and it's about to get on the 405 freeway, which is, to think about the 405 freeway, which you're seeing them get on the on-ramp here, being where this telescope, this $10, $11 billion telescope, is just driving in the middle of the night. That's crazy to me. It has to drive all the way down to Seal Beach. Again, this happened just a couple weeks ago. At that point, once it gets to Seal Beach, it was loaded onto a boat, just driving by some neighborhoods. There's a church here that just had no idea about, these people could have waken up in the middle of the night and just seen JWST just trundling by in the middle of the night. This all had to happen pretty secretly, because there was some worry about, it being damaged or, potentially even like kidnapped along this journey. But then eventually it gets to this boat, the MN Calibri, and it was taken by this boat up in the top right corner. You can see it all the way down through the Panama Canal to French Guiana, which is over in the bottom right here. And there was also a worry about pirates, literally pirates in the Caribbean, that would take the telescope, but that didn't happen. So we're very fortunate that it managed to get down there. But again, it was all pretty hush-hush about when this would happen and which boat it was on, but now we all know because it successfully got there. And so the next big step is we've tested the instruments in French Guiana, and now we're about to load it onto the rocket here, and it'll launch December 18th. And I hope you're excited about it. So what I'm going to do now is I'm going to finish and answer any questions you might have. Thank you all very much.
Thanks, Dr. Hainline.
Oh, I hear applause very light in the background.
So does anybody have questions that they'd like to have relayed to Dr. Hainline? So there's a question about how was this all paid for?
So this is a joint venture between the National Aeronautics and Space Administration, NASA, the European Space Agency, and the Canadian Space Agency. And so they're the primary people who put in the funding for this. NASA is funded entirely by taxpayer funding, and then Congress in their budget will budget a certain amount of money for NASA to do projects like this. So by being an American taxpayer, That's part of the money that went into this. And so NASA's projects are entirely funded. You can go look at their entire budget because they're a government organization.
Thank you. Other questions? Yeah. Why is French Guiana the launch location?
So if I move, let me shrink myself again. This is the Arianespace, which is a French company. This is their launch site in French Guiana. And so your question has kind of two questions in it, which is one is why was Arianespace used, and two, why French Guiana? Arianespace was used because the Europeans are our partner in this, right? They're a joint contributor to this, and they work with Arianespace, this French company, to do a lot of their rocket launches. Arianespace has an incredible track record of rocket launches. You probably never even pay attention how many rockets have launched from them. Just like a couple weeks ago, they had a rocket launch that was very successful. They've been very, very, very successful launching this specific rocket, and so it was chosen many years ago for that. But then the second question is, why French Guiana? Well, that's where they launch their rockets. But you want to launch near the equator because the equator gives you a little bit more oomph, right? Because you imagine on a ball rotating that the equator is moving faster than if you were to launch up near the top. This is why when we launched rockets like the Saturn V rocket, we launched them from Florida as far down south as we can. And French Guiana is very near the equator, where it gives it even more momentum. And so we have to use less fuel to get it out and get it going faster out on its journey towards L2.
Awesome.
These are great questions.
Okay, other questions? Yeah. There's a question about what happens to the parts of the rocket that come off, so all the space debris that's coming off.
Yeah, so in this case, most of the space debris, the fairings and the rocket parts, they fall to the Earth. They don't continue becoming space junk in orbit because they have not achieved the correct speed to become the type of stuff that would continue to orbit. And so most of this fall off primarily in the ocean. There's only recently have we, with people with groups like SpaceX and stuff, have we sought to go and reclaim a lot of these things. And I think in the space shuttle, there was some reclaiming of some of these as well. I can't remember off the top of my head, but most of it goes up there on a rocket, like the rocket that you see here, primarily like okay, this is going to be very silly, but I'm going to do this right now. Sorry, everybody. This right here, this and this are like just fuel, and there's a lot of fuel all in here because the engines are actually just down here. Like that's literally just the engine right there. So this is mostly just a big fuel container, and then the fairing, these two parts up there, so like if I go back a number of slides, let's go back like a bunch of slides to where's the slide I had? This is it. You can see how all the parts are here, and so you can see that these two are fuel, this is fuel, these are parts. Down here you can see how the fuel would sit inside of this solid and liquid fuel, right? And then these are parts relating to actually launching it, and these two things fall off. But all of these parts fall off and in our atmosphere and fall back to Earth. If you're interested in this sort of thing, if you're a person who's like, gosh, I really wish I understood more about how rockets work, and you're kind of a dork, there's a video game called Kerbal Space Program that allows you to put rockets together like this and launch them. And I think that they've made multiple JWST modifications to it to add JWST if you wanted to try your hand at launching JWST into orbit yourself. Other questions?
Yep. So this question is about how we point the telescope. So how exactly are they moving the telescope once it's in L2 to point at objects?
Yeah, so let's go back to this picture of the telescope. Here. So in the telescope, I'm going to do this again. Everyone finds it fun, and I think it's fun too. So this part down here is called the spacecraft bus. And this actually is the part that it does a lot of the electronics for talking to Earth using this, but also it's the part that has all of the ability to move and rotate the telescope, along with the fact that it has some momentum flywheels inside, these wheels that are spinning that help to if you're in space and you want to rotate yourself in a very specific way, you don't want to like you see in movies. You want to move it by using angular momentum that you've already built up inside of some wheels, and you have to dump it, but that's a more complicated thing. So all of the motion of the telescope for moving around is here. There are little jets that use fuel to keep it in its position in its orbit in case it strays a little bit. And that is actually what dictates the life of the telescope, is how much fuel we'll have left before it starts to drift away and we run out of fuel to keep it in the spot where it's supposed to be. We'll be able to rotate it because it uses solar panel to help charge up those flywheels. But in terms of actually keeping it where it is and not just be able to rotate, we need to have fuel. And so there's a limited amount of fuel in there. Now, I don't know if this is exactly what you asked, but I'm going to answer this anyway. To determine what we actually point at, once we actually decide, now that we have mechanisms to point at things, to determine what we point at, because this is a public, publicly funded telescope, the public, there was an open call for cycle 1, the first year of proposals last year, and people wrote proposals and submitted them, and there was a double blind, meaning that the people who were judging it were not able to see who was writing the proposals and vice versa, who was judging the proposals. No one was able to see either one. These proposals were all given equal weight and looked at, and a first year of science was decided on based on all these proposals. You yourself could write a proposal. It's very complicated to write a proposal, and most of the proposals, I think all of them, probably came from astronomy institutes or astronomy research places. But this was an open thing for people to write proposals and talk about the science they were planning on doing with it. And you can go look up all of the first years of science. And what that has done is it's essentially built a queue of science. After we do all of our commissioning, which is all of the things where we make sure that the mirrors are all pointed the right way, and because each one of them has little servos on the edges to make sure that we can focus it perfectly. And after we know that it's the right temperature, and after we know that all the instruments work, we do all that, then we start doing the science. And that has essentially been figured out already, and we just have a queue. And so JWST every day will have this is what I'm looking at today, and then the data will get sent back down to Earth.
Other questions?
Oops.
Yeah. So the question is, assuming everything goes to plan and it gets out there as expected, when do we expect it to start taking its first data? And I guess to add on to that, when do we expect to see the first public images?
Yeah, so the launch, if it goes right on December 18th, and it could be delayed by a day or two depending on weather, but we're hoping December 18th. It'll take about 3 to 4 weeks to get out to L2, and then we start the commissioning process. And I have on my desktop here the first commissioning schedule for the NearCam team, and I have to go out to Baltimore, where the mission control is 6 times over the course of the next number of months. But that will go for January, February, March, April, maybe even to June, maybe even into May, even into June. That's the timeline for commissioning, which is just making sure it's all focused and calibrated and the right temperature, right? You have to make sure that the telescope's going to cool off, the temperatures are all going to cool off in a certain way, and this has all been planned. I've had to rehearse this stuff 6 different times. I've had to go to Baltimore to pretend to do this commissioning because we want to make sure that when it actually happens, we're ready for it. And so you're not going to be able to see we're not going to be able to do the first science images until we're done commissioning. We know that the telescope, because we don't want to put out images that are out of focus or whatever like that. And especially if you're going to have your big coming out party, you want to make sure you're looking the best, the debutante ball of JWST. And so you're probably going to look for that in the late spring and early summer of next year. Fingers crossed. We don't know on the NearCam team, because it's guaranteed that the first images are going to come from NearCam. There's no way, I might be very biased, but there's no way that the first things that this public is going to see are going to be spectra, because that's not what you do. It's going to be beautiful images from NearCam. And so you'd think that on the NearCam team, we would be the people who are choosing that, but NASA keeps that information pretty close to the vest. And so we don't actually know what the first images are going to be yet, or what they're going to observe. And so we're hopefully next year you'll see them, and I'm hoping it's front page of the New York Times style stuff, or I should say front page of the St. George News, as a person who was just in the St. George News today. But pretty exciting images. And what you'll have to do is you'll have to bring me back next year so I can show you actual images instead of just what I've been showing to everybody, which is here's what we're hoping, here's the simulations. Next year around this time, I'll show you all sorts of beautiful images.
Nice. Are there other questions? I think we're getting pretty close on time, but.
In your wildest imagination, what would you most like to see the answer?
So, in your wildest imagination, Dr. Hainline, what would you most likely to see the answers to what questions?
Oh man. So in my most wildest imagination, what I'm actually hoping, I'll answer your question. Don't worry. It sounds like I'm gonna cop out on this question, but in my most wild imaginations, what I'm really hoping is that we find things we had no idea, new questions that like maybe someone in the room is like a scientist who, maybe there's like a fifth grader in the room who's like has no idea that they're going to be the person who uses the data from JWST to help solve these questions that we're going to introduce, right? Or data from future telescopes. So that's what I'm really excited about, is what we're not going to understand and what's new. But what I'm actually excited about that we are going to do is there's some big questions. I work in galaxies, and some big questions about things that happen in the history of the universe that JWST will have a unique insight into. When the universe made its first stars and galaxies, those stars and galaxies, what they did was they effectively, all the hydrogen in the universe at that point was what we call neutral, meaning that hydrogen is just a proton and an electron that orbits it. And early in the history of the universe, all the protons had little electrons orbiting them. Nowadays, if you look around the universe, that's not the case, because there's enough light that smacks into those protons with the electron to knock the electron off. And so everything is what we call ionized now. So something happened in the history of the universe to take it from neutral to ionized. And in the Big Bang, it was ionized. So this process we call reionization, because the universe is reionized. And we don't know exactly what did that. We have some ideas of what could be, and JWST will definitively answer that. It will say, it is this type of stars and these type of galaxies and these type of black holes. And that is going to be really, really exciting. And then on top of that, the survey I work on will at some point show us the farthest galaxy humans have ever seen. And that's going to be kind of a cool moment, because like I work on that team that helps define which galaxies are at which distance. And like there'll just be a moment where I'll be like on my computer being like, oh, there it is. That's the farthest galaxy humans have ever seen. That's the farthest thing. And like, I'll have to tell everyone, but for like a second, I'm going to like feel like really amazing about the advance of human understanding for like a little bit, and then I tell everybody and we write cool papers about it.
Awesome. Other questions? Yep.
Looking at like the atmosphere of planets, specifically methane, we'll be able to see if there's advanced societies.
So there's a question of when we're looking at the atmospheres of galaxies and we see certain elements, is there an expectation that we could potentially tell if there's life on those planets?
Yeah, so when we look at the atmospheres of planets, this is tough. And I am a galaxy astronomer. My office mate is an astronomer named Dr. Thomas Beatty. He also works on the NearCam team. And he's recently been having to temper expectations, even though I think he's also hoping. The problem is that astronomers aren't exactly on the same page as to what constitutes what we call a biosignature, like a thing that would be like, that's the smoking gun of life. And so there are things in atmospheres that would lead us to believe that there could be like that life is one potential source of that, methane or whatever, but the jury is still out. I am pretty bullish. I think that we have a pretty good opportunity, but also what's amazing is that JWST was not specifically designed for that task. It's doing it, and it's going to do a pretty good job of it. But there are other telescopes that are being designed for planet atmosphere detection and stuff like that. JWST is going to do an amazing job, but there's other telescopes that will help do that. If you are a person who gets really excited about looking for Earth-like planets and things like that, we are in a renaissance of like, we're just in the, I guess not a renaissance because there was no naissance. We are in like the golden age of doing that, and it's getting even cooler. But I think that JWST is going to have some pretty cool observations. It may not be immediate. It may take a little while for us to find more Earth-like planets that we can point JWST at. So I wouldn't expect in the first couple of years, but like give 5 or 10 years, and I think JWST is going to find some really cool things in atmospheres that we may, with some more evidence, be able to point to potential life outside of our solar system.
Excellent. Other questions? Yeah, so the question is about the sun shield and what the material is and how it's constructed, if it's like woven or.
So I hope you're not hearing the fact that I'm typing right now. So the sun shield is made out of a material. called Kapton. And if there's any like electronics buffs in the audience, they have used Kapton tape in the past. I have some Kapton tape when I have to do like, circuit board soldering and I want to tape things down. Kapton is a material that is like a plasticky like material that is really great in that it doesn't deform at very low temperatures. If you were to take some materials and put it at very low temperatures or high temperatures, it would warp a little bit. And so you use Kapton tape in a lot of electronics things and sensitive things because you don't want it to change its size and stuff. And you need this to be very tense inside of the very tense when it's at incredibly low temperatures and also warm temperatures on the bottom as well, right? A full range of temperatures, because as it goes through those 5 layers, it gets colder and colder and colder. And so what material would not change its shape between hundreds of degrees Fahrenheit to negative hundreds of degrees Fahrenheit? Kapton is a material that does that pretty well. As a result, it is not like threaded or woven or anything. It's like generating any plastic, right? Like you could imagine the way that you would make like large sheets of plastic for like cling wrap or something. That's kind of how you would generate one of these things. It's a very specific procedure.
Awesome. Other questions? Yeah. Oh, the question is, could you describe to the audience kind of what the Lagrange points are and how they work?
Yeah, let's do that. Oh man, let's do that with a diagram. Let's do that with this. We're gonna do a little. I'm gonna do the dance for it. It's gonna be tough because I'm here. So okay. Whoops, don't do that. Okay, so I'll make myself smaller here. Up here is the Earth, and the sun's way off in this direction, right? In this direction, and that direction, and Earth. And L2 is this point. There's not a thing there, right? It's just like a point in space. So if I make myself big again, if you imagine the sun is here and the Earth is here, the Earth goes around the sun, right? It goes around counterclockwise around the sun. And the reason that it goes around the sun is because it's falling towards the sun. But every time it falls a little bit towards the sun, it moves. It's moving very fast. And it wants to move in a straight line, but it's falling towards the sun every little bit. And so it just moves in a circle, right? So it's falling towards the sun, but every time it falls a little bit, it moves a little bit, and then falls, moves, and falls. And that makes it go in a big circle, right? That's what orbiting is. Orbiting is constantly falling while you're moving at a really high rate of speed, such that you just go in a big circle around it. And the circle, the size of the circle that the Earth is on, here, the size of this green circle is dictated by how fast the Earth is going. If it were going slower, it would probably go close. It'd have to be, it'd be farther from the sun, or else it would fall in, right? If it's moving a lot faster, it would probably be closer in, where like otherwise it would fly out, right? There's like a balance. The gravity of the sun and the gravity of the Earth together, combine those two gravities, there's a point, this point L2, that is a point where it is a stable orbit where an object would also move around, always on a line between the sun and the Earth is that point L2, and they move around. So like I'm doing the dance right now, I'm gonna spin around on this chair. It's gonna be hard to see, but they move around in a circle like that, right? And so JWST, this is the actual dance. We'll be doing this. And that L2 is a point where it's moving at a fast enough speed in its orbit where it's counteracted by the gravity of the sun, my head, and my hand, the Earth, right? So that's L2. There's also L1, which is a point between the two of them where the forces are counteracting each other in its orbit around. And then there's L3 and L4, which are on either side, and those are other Lagrange points. Named after a very famous scientist named Lagrange.
Thank you.
Yeah, you're welcome.
Other questions?
It's serviceable.
So the question is, if we were to get to a point where we could get out as far as that, would it be serviceable?
Right now, no. We don't have, like, NASA is currently not in the putting people out into space, like industry at the moment. there's plans for future potential missions to Mars or the moon, but really we don't have a space shuttle program anymore. We don't. We can put robots out, but JWST was not designed to be serviced because it's so far away. And when it was designed, we shuttered the space shuttle program, and the space shuttle program was never designed to go that far out, right? Like this is well beyond any human has ever gone, right? The farthest humans have gone is, you're probably aware, is like just on the other side of the moon, right? When Michael Collins and other people were orbiting, they would be like, farthest away that humans have ever gone, right? We've never gone 1 million miles from the Earth to service something like this. Like we don't have plans. We have some plans to go to Mars, which is much farther than that, but like it'd be a very, very difficult process for people to go out there, and maybe robotically. So there's there's no servicing plans now. Now, I don't know what the future might hold. I personally think that there's a lot of things that hopefully human beings can spend money on that would help us, socially and economically, just in terms of our health and our planet and the health of our planet, that we might want to spend money on before we spend money trying to go out and put more fuel in JWST. But let's imagine we solve a bunch of world problems. At that point, maybe human beings might go, well, okay, what else should we do? Oh, let's sit down and think about a way to go out and service JWST. But for right now, JWST has been entirely designed to like set it and forget it.
Okay. Other questions? Okay. Well, for me personally, I have a question. I know that it was designed with several redundancies, but can you talk about some of the redundancies in like the gyroscope or the flywheels and all of that?
Yeah, so I can mostly only speak to the redundancies in NearCam as a NearCam scientist. JWST is profoundly complicated, but NASA really wants you to build in specific redundancies because of the fact that things break, right? And like you're finding this out just this week with Hubble, and that Hubble had an issue with, it's gone into safe mode because of the way the data is coming through. But like they've also had issues with some of the things that keep it and it's able to move and stuff. And like you build in redundancies so that you can go, we're just going to power on this and it'll work. So Hubble was in safe mode earlier this year, and they switched to a side B version of redundant thing, and it started working again. And JWST in NearCam, there's entirely redundant electronic systems, so that if one electronic system shorts out or whatever, it's redundant. The fact that there's a NearCam A and B is technically also redundancy. So if one entire module stops working, we can still take NearCam images with the entirely separate NearCam module B or A. These redundancies are just like, they are pretty vital. There are issues, there are things with NearCam that are not redundant because they're designed to just work once. And I don't want to get into that very much because it terrifies me, honestly. But most of the important things that might be used, like on with NearCam and with some of the other things at JWST, have full redundant backup systems. And let's hope we never have to use them. But maybe down the line, issues might arise. This is the sort of thing that has happened to many space telescopes, like the Kepler Space Telescope had to stop being used well after its lifetime because it lost the ability to have one flywheel. What's cool is that scientists are pretty smart, myself not included, but most scientists who aren't me are pretty smart, and they come up with really clever ways of working with the telescope and an instrument despite things breaking. For instance, when Kepler, this incredible instrument that was looking for transiting exoplanets, when the flywheel stopped working, they said, what can we still do if we're only allowed to move in one dimension, right? Like, so you could imagine that, JWST, some key part of it breaks down the line in the future, and we go, all right, what can we do while these things don't work, right? And that's going to be really, that'll be something where I won't look forward to that, but I know that we're resourceful and pretty clever about this. I can see some of you. Hi, everybody. Hi. There we go. Good. You should all come down to Tucson at some point. I've been to Bryce Canyon. It's so beautiful. I'm so jealous of you all. I mean, I like Toronto where I'm at right now, but I just, it's a really beautiful site, and I'm really excited to have been part of your day's exploration. And hopefully it's clear and you can go outside at night and look up at the stars and wonder. And if it is clear, look for Jupiter and Saturn in the south. They're pretty bright this time of year right now. It's a fun time to be excited about JWST, and wait for the launch next year, December 18th. It'll be like really early in the morning for us here over in this part of the country, like 4 or 5 in the morning. But hey, if you go to NASA's website, I guarantee you'll find the NASA like live stream of the launch, and just fingers crossed.
Well, thank you, Dr. Hainline. Sorry, we just had a quick change on the mic battery. So, but we want to thank you for talking with us today, and hopefully we'll see you or somebody later on this next year to see some of the first images.
Yeah, invite me back. Invite me back. I'd love to come talk with you in the future.
Thank you. Have a good evening.
Bye.